Okay, so welcome back. So at the end of the last lecture, I had talked a little bit about systems of linear equations, okay, and how we were going to use matrices to solve them. So today we're going to, take that a little more seriously and give some more details, okay? So let me write down the general picture here. So we're going to have m linear equations. And n unknowns, okay, so n variables, which are usually going to be x1 up through xn. And then a general system looks like just like a11 x1 plus a12 x2 all the way up to a1n xn is b sub 1. Okay, so let me just note here the a sub, in general, ij, and the b sub I are going to be elements of our field. Okay, so you can think of the real numbers, complex numbers. Sometimes you want to restrict everything to be rational. In any case. Okay, and then, so the next equation it's again the same variables, just different scalars. Up to a2n xn is some scalar b2. And then this goes up to the mth equation, where we denote the scalars am1 x1 plus am2 x2 all the way up to am n xn, okay, is b sub m. Okay, so there's what we want, well, is we'd like to find x1 up through xn, which are going to be elements of the field. Okay, so you want to find the numbers that these variables can be, which satisfy all of the equations, okay, simultaneously. Okay, and then, so of course you want to find a solution, and then you might want to understand all solutions. Okay, so if there's more than one of these. Let me just note here that this, in general, the space of solutions is not a subspace. Okay, so you can't add two solutions and get another solution or multiply by a scalar. I mean, for example, the zero vector is not generally a solution to such equations. But we'll see that you can often understand the space of such solutions, even if it's not a vector subspace. Okay. Now, the way that I've written the equations is obviously meant to inspire, introducing a matrix here. Okay, so we're going to let A be the matrix of coefficients. A11 up through A1n, AM1 up through AMN. Then if we think of these variables as just a vector in Fn, okay, so we think of x1 through xn inside f to the n, then we can think of this matrix as a linear transformation. And then you can see that the matrix multiplication is precisely, this gives you the system of linear equations. So really what we're trying to solve is we're given an m tuple of numbers, we're given an m by n matrix, and we want to know what n tuple we put in that gives us the desired output. Okay? So in other words, this matrix of coefficients induces a linear transformation okay, so A, which goes from, say, Fn to Fm, okay? And this is with choice of a basis. So let me just say with respect to a standard basis. Okay, so if I'm thinking of Rn, I'm just taking coordinate bases. Okay, and what we'd like to do is we want to understand the preimage of the vector b1 up through bm. Okay, so for this linear transformation, of course, I could take a different basis. This would give me a different system of equations. And we'll see that that's going to be an important concept when we want to try to solve these. Okay, so maybe I'll just note here. I mean, this is kind of the reason. So if b1 up through bm is the zero vector, okay, then the set of solutions is a vector subspace. Okay, and this you can easily check. If you have two things which get sent to zero under a linear transformation, you take the sum of them, or you multiply them by a scalar, you're going to get something which still goes to zero. Okay, this is usually called the kernel. Well, not usually, always called the kernel of the linear transformation. But in general, you don't have a subspace because you're having some linear transformation. You're picking some vector, seeing what gets mapped to this. And this could very well just be like, a single vector over here. I don't know. This vector here is the only vector that gets sent to this line, or to this point. Okay, so we'll see also that you have more structure in general. You know more of what the space of solutions look like. Okay. Maybe I'll just also note, you can also think about this as finding intersections of hyperplanes in Rn. Okay, so this is a usual, if we have a system of linear equations, say two variables, two equations, then we think of this as a transformation of R2, or you think of each equation, so alpha 1 x1 plus alpha 2 x2 is B, and beta 1 x1 plus beta x2 is C. But these determine two lines, and the solution to the set of equations is the intersection of those. Okay? Or you could have systems where the lines are parallel and you get no solutions, or the lines match up exactly and you get infinitely many. Okay? And in general, the picture in R3, which I'm not going to do a terrible job drawing, is you have a bunch of, let me try different colors, a bunch of planes now instead of lines in R3. They intersect in some potentially complicated way. Okay. Each plane corresponds to the solution set of one equation, and then their intersection corresponds to the points that satisfy all the equations. Okay? So again, this is something that we will see more of soon. Okay? So let me give you the usual notation for this, or the notation that we're going to use, which is we're going to have the matrix A here, and the matrix, the vector b1 up through bm here, And this determines essentially the whole problem, right? So the whole system of linear equations is determined by this matrix, okay, where you've indicated what part is the coefficients and what part is the output vector. Okay, so now we'd like to, try to solve this equation, okay? So let's notice, the first useful thing to notice is that if you have the equation ax equals b, you can take any m by m matrix and look at the new equation EAX is equal to EB, okay? And the claim is that, well, the solutions to AX equals B are solutions to EAX equals EB. Okay, so what is actually going on here? Well, we think of A as going from Rn to Rm, and then, so this is A, oh, okay, I'll put it here again. Here's A, here's E, going from Rm to itself, okay? And then, well, you can take an element, X. If it's a solution, then it goes to B. And then, of course, if it's, B just sends it to EB, okay? That's where it goes. So, if you're looking at the composition and saying what things map to EB, well, certainly all the elements X will be there, okay? On the other hand, notice that this might be strictly larger, so there might be more solutions here. Namely, if E is not injective, there might be some C, which also goes to EB. And, then you're also picking up the solutions, all the X that go to C, okay? On the other hand, if E is an invertible matrix, so an invertible linear transformation, well, then there are no more C's, right? The only thing that gets sent to EB is B, okay? So the solutions to AX equaling B are equal to the solutions EAX is equal to EB, okay? So what we'd like to do is, work out invertible transformations that we can use to make the equation different and hopefully simpler, okay? So there turn out to be three important classes of invertible matrices. Okay, so these are not going to change the solution set, and they also correspond to, which I'll mention, operations on the system of linear equations, which makes it quite obvious that they're not changing the set of solutions. Okay, so three classes of invertible matrices. So the first one is given by, well, let's see, so it's the identity matrix, then you have a 0, 2 zeros. Okay, I'm trying to describe this. You take the identity matrix, there are 2 zeros, okay, in say the ith column and the jth column, and then you put 1s here. So in other words, you take IM, you replace the ith and jth ones by zeros, okay, and then you put 1s in the spots Aij and Aji. Okay, so let me give you just a 3x3 example of this. So it looks like 1, 1, 1, but then you put 1, 0, 0, 1, 1. Okay, this would be the first class of invertible matrices. You can do this for all I not equaling j. Okay, so what does this do? Well, on the level of matrix multiplication, this switches the ith and jth rows of A. Okay? So one way to kind of always check this is, well, see what this matrix does when you multiply it by the identity. Okay? Of course, it spits out the same matrix, right? 0, 1, 0 times the identity is just, well, it's the matrix you started with. But this is precisely the identity matrix with the second and third rows switched. Okay, this is just in, or I3, with the second and third rows switched. Okay, in general, that's what it does. Okay, so that's something you can do, and notice this obviously doesn't change the solutions to a system of linear equations, right? You're just changing the order of the equations. Okay, so what you should check is, well, I said this was invertible. Again, we haven't really worked out how to invert matrices. So in this case, I claim it's easy. And from this kind of description, you should be able to work out exactly what the inverse is. Okay, so I'm going to just leave this as a good exercise to think about. Okay. Another operation that you can do is you can take any matrix and multiply it, replace one of the ones in the identity by an A. Okay. What this does is it multiplies the ith row by A. Okay. Again, you can just check this by thinking about what it does to the identity matrix, and it turns the identity matrix into this one, and the ith row is multiplied by A. Okay, and you can do this for any row. Again, this won't change the system, or it won't change the solution space, as long as you remember to not only multiply the coefficients by A, but also the output vector. So if I take A I1 x1 up through A I n xn is B sub I, this is part of a system of linear equations, and then I multiply both sides by A, well, then I still get a solution. Okay? And that's what's going on. That's what's going on here, right? I'm multiplying the B, or the ith entry of the B vector by A, and over here I'm doing that. Okay. Finally, there is one where you take the identity matrix, leave it as it is, and then you put B in a space where so everything else is 0, except for one non-zero entry, B, which is in, say, the ijth slot. Okay? And what this does is it adds the ith row multiplied by B to the jth row. Again, you can see this is exactly how I obtained from the identity matrix to this one, is I multiplied the ith row by B and then added it. Okay? So again, you can check this won't change the solutions to a linear equation. And you should also check in both cases that these are invertible. Okay? From these descriptions, it's easy to work out what the inverse has to be, and you can again write it down as an m by m matrix. Okay, so you might, at this point, be reasonably suspicious of these matrices. So you might ask, why are we considering these ones? Okay, well, so these matrices, well, they generally are easy to work with. Okay, in the sense that if you multiply, with these matrices, you know exactly what you're doing. Okay. And on the other hand, and it will turn out that any invertible matrix, okay, so will turn out to be a composition or a matrix multiplication of such linear transformations. So it will be a composition or multiplication of these matrices. Okay, so in a sense, we're not missing out on any possible way to solve a system of linear equations, right? If you are looking at matrices EA, X, EA is EB, then this E is actually equal to E1 up through EM, where the matrices, where every one of these matrices is of the form as above. Okay, one of those types. And actually, you can make this quantitative. A is going to be a product. If it's M by M, it's a product of less than or equal to M squared E sub i's. Okay? So you don't have to use a ton of these matrices. It's just given to you by, how many equations there are. Okay, so let's see an example of how to use these operations to solve a system, okay? So I'm going to give essentially random numbers, which are small, so they're easy to compute. So I have x1 plus x2 plus 3 is 1, 2x1 plus 3x2 plus x3 is 1, negative x1 plus x3, so I'm thinking plus 0, x2 is equal to 5. Okay? So then the matrix that we get from this is just the coefficients and the vector that we're aiming for. So we get 1, 1, 1, 2, 3, 1, negative 1, 0, 1. So in this case, we're going to use these operations to turn our matrix, coefficient matrix, into something which looks what's called triangular form, because it's going to have zeros in the bottom left. And in general, we'll see this is, say, putting the matrix into what's called row echelon form. And then we'll see you can put it into what's called reduced form, and in general. Okay, so that's the general terms. So let's see what we do. Well, so we need to make these terms into zeros. This helps solve the equation. So we're going to add minus 2 times the first row to R2 and add the first row to R3. Oops, hard not to make it coordinate vector space R3. Okay, so we have the first row stays the same. This is the general procedure. This will go to 0 by construction. Then we're adding minus 2, so it goes 1, minus 1, minus 1. Then we're adding row 1 to row 3, so we get 0, 1, 2, 6. Okay? Now we're going to want to do the same thing, use this 1 to cancel this 1. Okay, so we add minus row 2 to row 3. Okay? So again, we have to do this also for for the vector in the image, okay? So what we're getting, now this stays the same. Now the second row also stays the same. We're only changing the third row, and we get 0, 3, 7. Okay? And now from this, we can easily solve, we easily get a solution to the system of linear equations. Okay, so in particular, now the third equation looks like 3x3 is equal to 7, so x3 is 7/3. The second equation now is x2 minus x3 is minus 1, and we know x3, so we have x2 minus 7/3 is minus 1, so x2 is equal to 4/3. Finally, the first equation looks like x1 plus x2 plus x3 is equal to 1, and we know this is x1 plus 4/3 plus 7/3 is equal to 1, so x1 is minus 8/3. Okay, so that's the solution. Okay, hopefully I've done my maths correctly. All right, and so notice what we were doing at the end was really, you could also think of this as converting this matrix into an even easier form, or a better form to read off the solution. Okay, so let me note that now we're going to go to what's called reduced row echelon form. I'll make this larger. We can now add minus row 2 to row 1. Okay, so now we've kind of gone down here, and now we're going back up. Okay, and by going back up, I mean we're going to make term 0. Eventually, this will just be the diagonal matrix. Okay, so we add minus row 2 to row 1, so we get 1, 0, 2, 2. Okay, 0, 1, minus 1. Everything else stays the same. Oops. Then we add a third of row 3 to row 2, and minus 2/3 of row 3 to row 1. Okay? So the good news is now I know exactly what this matrix is supposed to be. It's just 1, 1, 1, zeros everywhere else. And then here I have to check what I get for my answer. So I'm getting a third row 3 to row 2, so that's 7/3 minus 1, so I get 4/3. Oh, also I guess I multiplied row 3 by a third. Okay, sorry, that got me the 1. So this goes to 7/3. Then I added minus 2/3 of row 3, so it's minus 14/3 to 2, which is precisely minus 8/3. Okay, and now my system of equations is just the simplest it can be. x1 is minus 8/3, x2 is 4/3, and x3 is 7/3. Okay, so once you've kind of reduced it to this form, trivial to write down what the solution is. Okay, so this brings us to, what these forms are called. So this is called echelon form. So I'm just going to draw the general picture of what a matrix looks like. It doesn't have to be square, so this is some m by n matrix. Okay, so the first thing what you'll see, if it's in this form, and you can go to the book and it'll have the precise formulations. So you'll see some number of rows of all zeros at the bottom of your matrix. Okay, there might not be any, but if there are 0 rows, then they'll be at the bottom. Okay, so remember these rows with all 0 entries, essentially, that corresponds to trivial equations. Okay, in some sense, we're pushing all the trivial equations down, okay, and focusing on the non-trivial ones. All right, then what happens is you might have start getting rows of, or columns of zeros. Eventually, in the top row, okay, you'll see your first non-zero entry, okay? Then you don't know anything after that. It might be 0, might not be, all right? Then what's guaranteed is that for any row below this, there's all zeros, and there might continue to be some zeros. Okay, so the first non-zero entry of the second topmost row is strictly to the right of the non-zero entry of the first row, and then you have no idea. Okay, and then there's the same thing. 0, maybe this is non-zero, no idea. 0, 0, no idea, and so on. Okay, that's the general picture. So these are called these non-zero entries. So the first non-zero entries in the rows are called the pivots. Okay, and these are, when we were doing our operations, these were the terms that we were using. I'll bring this up here just so you can see again. Oh. So these were the terms that we used to cancel all the other terms in the row. Okay, or sorry, in the column. So we wanted to take a column and make all the entries but 1 0, and the pivots were the non-zero terms that we used to do that. Okay, and then I'll draw the picture for reduced. So there's what's called reduced echelon form. Okay, which is, well, so first it turns all of the pivots into ones. Okay, so we know that we can do this. So it's the same picture. You might have rows of zeros, you might have columns of zeros. All the pivots are going to turn to 1. We know that we can do that because we can multiply rows by any number. Okay, so this will still be 0. Then you might again see a 0. This might be something which you can't control. This is now a 1. This is a pivot. And now this, if you're a pivot, all the entries above and below the pivots are 0. Okay, so all entries above the pivots, which are now equal to 1s, are 0. Okay, and this is above and below because you've put it into echelon form, so you've made everything here 0, and then you go and cancel the terms above it. Okay, and then so you're not exactly sure what's going on. Every time you see a pivot, though, you're going to get zeros, but there might be non-zero terms somewhere in the rows depending on whether you can cancel them or not. So there might be, this might be a 0, those might be non-zero, okay? But that's the general picture. Again, the book will give you precise formulation. Okay, so let me do an example of something in reduced form. I mean, I did one which it was 3 by 3 and which just gave us the identity matrix, but maybe I will give one which looks a little bit of a different form. Okay, so here, I don't know, I might have a row of zeros. Okay, and now I'm just adding in the vector on the side. I mean, so the reduced echelon form is about this matrix, or same with echelon form, but of course you can keep track of the vector that you're trying to find, okay, or to hit in this linear transformation. So you might have this row of zeros. This might be like 1, 2, 0, 0, 3. Then this has to all be zeros. This can be, well, now this has to be a 0, right, because there's a non-zero term here. This could be a 1, 1, 5, 0. Nope, no, I didn't have to make this a 0. So you shouldn't make these as you go. Okay, there we go. So this, and I'll just put some random numbers here. This is a perfectly good matrix. in reduced form. And now what we'd like to do is read off the solutions to it. Okay, so the efficient way to write this picture is, you remember, so this is the x1, x2, x3, x4, x5. You remember the coefficients. So in your system of linear equations, this is secretly not, I mean, it's not 2, it's 2x2. And what you do is bring the terms corresponding to columns without the coefficients, or without the pivots, over to the right-hand side, okay? The point of this is that, well, when you have, if you've removed everything that's not a pivot, you're going to see something very close to the identity matrix, essentially the identity matrix and some zeros, rows of zeros on the left-hand side, and then you could just solve for the right-hand side, but now, of course, that's in terms of other variables. Okay, so let me just do it. And I realize, sorry, I'm going to make this larger, okay? So we have 1, 0, 0 is going to give me 5 minus 2x2 minus 3x5. Then I get 0, 1, 0. Okay, I guess I made it bigger than it was necessary, is equal to 3 minus 5x5, 0, 0, 1 is equal to 4. And then finally I get rows of zeros equaling 0, which doesn't contribute anything, okay? Or just stays the same. All right, so therefore my solution is, well, I say x2 and x5 can be any real numbers or any elements of F, whatever field I'm working over. And then I know how to solve for the remaining variables. So those can be anything. And then I get x1 is equal to, 5 minus 2x2 minus 3x5. X, and you have to remember now this is x1, x3, and x4. x3 is equal to 3 minus 5x5, and x4 has to be 4. Okay, so that's the general description of the solutions. I could write these equations in equivalent ways, but that's the general formula. Okay, so now let me start talking about what the space of solutions look like. Okay. I mean, what we would like to know is generally, if I look at this reduced form, when do I get a solution? And then how many are there? Which will usually correspond to, sorry, I'll just bring this back up. I mean, this usually corresponds to how many variables can be free. Do I have any choice of my elements of F? Okay, so we'd like to know kind of how many free variables we have. And then, of course, you also want to know what their actual solutions are. Okay, so the first thing we'd like is a criteria for no solutions. This turns out to be relatively simple. So you suppose you have your system, you've reduced it to reduced echelon form. So everything is going to be kind of a criterion for what these end up looking like. So you might end up over here with a row of all zeros. This happened in the last solution. But there's no reason that, B, okay, there's no reason that the term here has to be 0. Okay, if it is, we're happy. If not, so if there exists this row that looks like this and B is not equal to 0, then there's no solution. I mean, this is clear, okay? And this is actually if and only if, okay? I won't go through the formal proof of it. I mean, essentially, if you don't have a row that looks like this, you go to this, you do this procedure, and this will produce for you a solution. Okay, so the only way that this procedure doesn't give you a solution is if you have a non-zero term here. If you have a 0 there, then you can automatically just find a solution in the same way we did. Okay? Okay, so I'd like to just give the geometric picture here so we don't completely lose our intuition for what's going on. So let's think of A as this matrix with all zeros. Okay? And now we think of A as going from V to W. Okay? Determine some linear transformation, and we've chosen a basis of these, so we write down the matrix. Okay, so what does it mean? And this can be, at this point, just anything. Okay? So what does it mean for there to exist this row of zeros? This means that the image of every basis vector of V has a 0 coordinate for some basis vector of W. Okay? So therefore, let me just draw this. If it was going from, say, R3 to R3 in the standard basis, okay, then what it would say is every basis vector will get sent to a basis vector with 0, say, z coordinate. Okay? So all the images of the 3 basis vectors, I don't exactly know what they are, but I know they have to be in the xy plane. And therefore, this is then true, since this is a linear transformation, it's true for any vector in V. So any vector V in V will have image that has also 0 coordinate. That has image with the 0 coordinate for this basis vector. Okay? So in other words, the image is going to be contained in a hyperplane of smaller dimension than the ambient vector space. Okay? And therefore, if you're trying to, if I'm writing now, if I was thinking about this and I put anything here and I had a b not equal to 0, I would be trying to find a vector which mapped onto something in my range with non-zero coordinate in the z direction. Okay, but this is not what's going on, right? Every basis vector, and hence every vector, is getting sent to this hyperplane, so the image misses every vector that has non-trivial z coordinate. Okay, so now that we have, let's suppose we aren't in that situation, so we have a solution. Now we'd like to know when there's unique solution. Well, this corresponds to no free variables. Okay, which is the same as saying every column has a pivot. Okay, after row reducing. So putting in row reduced echelon form. Okay, so the pictures might be, say, look something like this. So it could just be one that we saw before, where you got the identity matrix on one side, and then ABC on the other. Easy to solve, and it's easy to see there's a unique solution. You might also have something like this. So a row of zeros. Now, if there was a non-zero term here, we wouldn't have a solution. So you might have a 0 there. And then you'll still get a unique solution, which again you can just read off. Even though there are more equations than variables. Okay, and for now, I'll just say otherwise, there are infinitely many solutions. Well, as long as our field that we're taking is infinite. Okay, so if f is. You can think of this, it's kind of fun to try to do the same type of row reducing over the field f2. Okay, I'll leave that as fun exercise. You know, start reducing matrices over f2 and see what you get. It's essentially the same procedure, works. So in any case, there are infinitely many solutions, and okay, and you know, more coming. Okay, so I won't exactly say everything now about what this space of solutions looks like. But if you have an infinite field, once you have a free variable, you'll have infinitely many solutions. Okay, so let me end now with one proposition, and we'll come back to it in the next video. It's essentially applying this reduced form to a very specific matrix where you are mapping Fm to Fn by sending m vector, the standard basis, to m vectors. Okay? And then properties of the matrix should tell you properties about these m vectors. Okay? So we're going to let A be the matrix. It's going to be n by m. Columns are going to be the v sub i's. Okay? Up through v sub m. We want to reduce this, put it into echelon form, and tell us, you know, what does that tell us about the vectors? Okay? So it turns out you can make kind of complete statements here. So we have the v1 up through vm is linearly independent. Okay, if and only if the reduced form has a pivot in every column. Okay. The second one is it's spanning if and only if you have a pivot in every row. Okay. And then it's a basis if and only if you have a pivot in every row and column. Okay, so let's prove this. So we'll start with one. So first note that linearly independent is exactly the same as saying that AX equaling 0 has a unique solution. Okay? The linear combination, any linear combination of the VI's is of this form. Okay? And therefore, that's just, you know, a unique solution was the condition that we had a pivot in every column. Okay, so that's just a translation of that statement for the specific vector of 0. Okay, for spanning, it's going to be similar. So here v1 through vm is spanning exactly when ax equaling b has a solution for every b. Okay, but then notice if you have a reduced form, and then you have a row without a pivot. Okay, so I'll just say this is row of zeros. And if I put b here, which is not 0, then I won't have a solution, okay? And then we saw that there was, if I had a pivot in every row, then there is the formula for solving it. Okay, so otherwise, so b, if we have this row of zeros, I can produce a b with no solution. Okay, otherwise, the formula for producing solutions works. Okay. Okay, and that formula just happens if and only if you have a pivot in every column. Oh, sorry, every row. Okay, and finally, this last condition is saying that it's a basis exactly when ax equaling b has a unique solution for all b. Okay? And therefore we have no free variables and no rows of zeros. Okay, so therefore we get pivots in every column and row. Okay, so that's essentially just putting the last two conditions together. All right, so I think I'm going to stop here, and then in the next video we're going to begin doing some corollaries of this proposition, some things that we haven't made explicit about bases or generating sets. So anyways, stop there. Thanks.